A wooden crate of mass 20 kilograms is pulled in a straight line along a rough horizontal floor using a handle attached to the crate. The handle is inclined at an angle alpha to the floor, as shown in figure 1, where tan alpha is equal to 3 over 4. The tension in the handle is 40 newtons. The coefficient of friction between the crate and the floor is 0.14. The crate is modelled as a particle, and the handle is modelled as a light rod. Using the model, Part A asks us to find the acceleration of the crate. So, first of all, since we've been given all this information, it might be best if we can try and visualize it a bit better by marking it on the diagram. So, first of all, if we know that the crate has a mass of 20 kilograms, we know that it must therefore have a weight of 20g, since F, force, which in this case is weight, is equal to mass times acceleration. The mass is 20 kilograms, and the acceleration is gravitational acceleration, which acts downwards, and we can call this g. So we have a weight, and therefore we must also have a reaction force. This acts perpendicular to the plane, and if we just call it r, we don't know what it is, but we know it acts in this direction. We're also told that there's a coefficient of friction and that the floor is rough, which both tells us that there is a frictional force, and if the crate is moving in this direction, in the direction of this arrow, then the frictional force must act against that. So if we say that it acts in this direction, and if we just call it F for now, again, we do not know it just yet. And now the final thing that we can mark on this diagram is this 40 Newton force, this tension in the handle. It might be easier for further calculations if we componentize it into a vertical and a horizontal component, because given that this arrow, and this arrow are all acting either vertically or horizontally, all our calculations are going to be in these two planes, and so it would be best if we can also write this force in these two planes. So if we start with vertically, if we were to use trigonometry, this is a right angled triangle. The hypotenuse is this, and it has a value of 40, and the angle is alpha. So if we're using the opposite in the hypotenuse, this is the sine rule, where sine alpha is equal to opposite over 40. If we rearrange that, we know that the value of this component is 40 sine alpha. And if we do the exact same thing with this horizontal component that acts in the same direction that this arrow does, we now need the cosine rule. And so here it would be 40 cos alpha, using the same principles we did for this vertical component. So now that we've got all of this information a bit more easy to visualize on our diagram, we can start to try and find out some of these values. So the first value that we don't know is this reaction force, R. So if we went to find this, if we were to resolve in the direction that R acts, which is vertically upwards, we resolve vertically upwards. This is using the equation F equals ma. So if we start with the forces, the left-hand side, we know that the force is acting in the direction of R. This force here, which is R, and also this component of the tension acts upwards, 40 sine alpha. So we know that acting in this positive direction is R plus 40 sine alpha. However, we also have a force that's acting against this, and we could say this is in the negative direction if we're resolving upwards, and that's this 20g, the weight of the crate. So we could write this as take away 20g, and that's now the kind of net forces if we're resolving upwards. Now force is equal to mass. We know that the mass is 20, but we know that the acceleration when we're resolving upwards is 0. The crate isn't moving upwards, and so it's not accelerating upwards. And so 20 times 0 is 0. So we know that this is all equal to 0. And so we can see that now, in our equation resolving upwards, we have two unknowns because we have an r, but we also have an alpha, and we need to find what one of these are before we can solve the equation. Now, in the question, we were told that tan alpha is equal to 3 over 4. And what that means is we can draw a right angle triangle to represent this. So if we drew a triangle like this, where this is the right angle, and if we just call this angle alpha, it doesn't really matter which of these two angles we call alpha. If tan of alpha in general is equal to the opposite over the adjacent, and we've been told here that it's equal to 3 over 4, this means that the opposite must be 3 and the adjacent 4, because here we can see that tan alpha would be equal to 3 over 4, which is what we've been told. So using this, we can now use Pythagoras' theorem to find this final missing side of the triangle. We know that the square root of 3 squared plus 4 squared is equal to 5, so that this is now 5, and so we have a full right angled triangle, and from this we can use trigonometry to find a value for sine alpha and cos alpha, as well as tan alpha, which we already have. So if we start out with the one we know, tan alpha is equal to opposite over adjacent, which here is 3 over 4, which we have been told, but it's kind of a check of whether we've done this correctly, since we've got the same as the question. Now, sine alpha is opposite over hypotenuse, and here we can see that the opposite to this angle alpha is 3, and the hypotenuse is 5, so sine alpha is equal to 3 over 5. And lastly, cos theta is adjacent over hypotenuse. Adjacent here is 4, hypotenuse is 5, so cos alpha is 4 over 5. So now we have values for all of these. We can substitute in to this equation where we have 40 sine alpha. We can substitute in that sine alpha is equal to 3 over 5. And then, if we were to do this, we'd end up with r plus 24 take away 20g is equal to 0. So now, if we were to rearrange this to get r as the subject, we would add 20g to both sides and take away 24. And if we did this and then solved it in a calculator where g is 9.8, we would find that r is equal to 172 newtons. So this reaction force here is 172 newtons. So now that we've found this, we can actually go on to finding the acceleration of the crate. And the reason for that is because of the equation that states that the frictional force is equal to the coefficient of friction multiplied by the reaction force. And so we know that this frictional force here we don't have a value for, so this is just F. However, we were told in the question that the coefficient of friction between the crate and the floor is 0.14. So we know that the coefficient of friction is 0.14, which we represent with a mu in the formula. And then this is multiplied by R, which is this force here, and the one that we just found to be 172. So we know that the frictional force is equal to 0.14 multiplied by 172. And so we can actually find this frictional force. If we do this calculation, we find that the frictional force is equal to 24.08 newtons. And so now we have a value for all of the previously unknown things in this diagram. We have R, we have F, and we found a way that we can solve things with alpha in them because we have equations for cos and sine alpha. So now that we have this, we can find acceleration because we can make an equation and solve it. So since the crate is moving this way, it's moving horizontally along the floor, that means this must be the direction of the acceleration. And therefore, we would resolve in this direction, which is horizontally to the right on the screen. And so again, using F equals ma like we did before, we know that the forces acting in this direction, if we went back to the diagram, the forces acting in this direction positively are 40 cos alpha. That's the only force that acts in that direction. And then the forces acting against this direction, there's only one again, and that's this one, F, that's acting in the negative direction when we resolve to the right. So we can write the forces, so on the left-hand side, we would write this as 40 cos alpha and then take away F, which we've just found to be 24.08, but if we write it as F at the moment, so take away F, so this is the net forces when we resolve in the direction this arrow here, and now this is equal to the mass of the crate is 20, and then the acceleration is what we're trying to find, so if we just leave that as A, because this is what we're solving for. So now we know that cos alpha is equivalent to 4/5, as this is what we've found up here at the top of our workings out. So we can rewrite 40 cos alpha as 40 multiplied by 4/5, and this is equal to 32. So we have 32 take away 24.08 equals 20A. And so if we do this calculation, just 32 take away 24.08, 28 is equal to 7.92. And then when we divide by 20, we can find that the acceleration is equal to 0.396. And then acceleration is measured in meters per second squared. And this is our final answer. We found the acceleration of the crate is 0.396. So this question is worth 6 marks, and we get our first 2 marks come grouped together, and they come from resolving vertically. So that's this first thing we've done here, resolving vertically upwards. And the reason we get 2 marks for this is we get a method mark for simply doing it, so just for resolving vertically, regardless of the answer that we then ended up with, we get a method mark. And then we get a further answer mark for doing it correctly, and ending up with this expression up here. So this is 2 marks, a method, and an answer mark. And then we get a further 2 marks for doing the exact same thing horizontally. So attempting to resolve horizontally gets us a method mark, and then doing it correctly gets us an answer mark, which is what we've done here. So that's another 2 marks. We also get a mark for finding the frictional force, so knowing that the equation is the frictional force is equal to the coefficient of friction times the reaction force, and then knowing that what the coefficient of friction is and the reaction force, and solving that. So this gets us a further mark. And lastly, we get an answer mark for finding what the acceleration is. So stating that A is equal to 0.396 meters per second squared gets us the last mark available for this question. The crate is now pushed along the same floor using the handle. The handle is again inclined at the same angle alpha to the floor, and the thrust in the handle is 40 newtons, as shown in figure 2 below. Part B asks us to explain briefly why the acceleration of the crate would now be less than the acceleration of the crate found in Part A. So we can see the difference between figure 1 and figure 2 is that in figure 1, the tension acts outwards in this direction, out and up, whereas in figure 2, the thrust is now acting in towards the crate, and it's acting downwards. So if we were to draw onto the diagram its vertical and horizontal components like we did in figure 1, unlike figure 1, its vertical component is now acting downwards instead of upwards. And similarly to figure 1, the horizontal component acts horizontally to the right, so in the same direction, because the crate is still moving in the same direction. It's just that the handle is now in a different position, which affects the components. So in part A, the first thing we did was calculate the reaction force, which is this force acting upwards here, just as it is in figure 1 up here. So the first thing we did was calculate the reaction force, and in figure 1, for the forces in the F equals ma equation, acting upwards, we had R and this component of the tension, and then we had the weight acting downwards, whereas if we add the weight on as well. In this figure 2, if we were to do the exact same thing, resolving upwards, we would have R acting in this direction, but then we would have this component and the weight both acting against it, instead of just the weight acting against it and the vertical component acting in the same direction. So now we have less things acting in the same direction as the reaction force. And since it was this is equal to 0, the forces were equal to 0, if there were more things acting in the negative direction when resolving upwards, this would increase R. And if R increases, so does F, because of the equation F equals mu R. An increase in R, where mu is the same, leads to an increase in F. So now our frictional force has increased because of our reaction force increasing. And now if we think back again to A, the formula we used in part A to find the acceleration was the horizontal component of the thrust in this case, but tension in part A. Take away the frictional force is equal to 20 times the acceleration. So we were taking away this frictional force from the horizontal component. So if this frictional force is now increased, we're now going to have a smaller number on this side of the equation, and therefore dividing a smaller number by 20, because it's F equals ma, mass is 20. So if the net value of force when resolving horizontally, if that's decreased, and we divide that by 20, it's going to be a smaller value than what it was in part A, because this net force is decreased due to an increase in the frictional force. And therefore, this will lead to a decrease in the acceleration. So if we were to write that out, we can say that if we pushed the crate along the floor, the reaction force R will increase due to the vertical component of the thrust, this 40 Newton arrow. The vertical component now acts downwards, and therefore this will cause the frictional force to increase, as we said, because of the F equals mu R equation. And if the frictional force increases, the acceleration A will decrease. And this question is worth 2 marks, and we get our first mark for saying that because we push the crate, R, the reaction force, will increase, and this will therefore increase F, the frictional force. So that gets us first mark, if we were to mark it on around here. And then we get our last mark for saying that if we increase F, this will cause A to decrease, so concluding that A will decrease in total. This will get us both marks.